Hi students, this is our third lesson for the topic of vectors and applications of vectors for the International Baccalaureate course Analysis and Approaches. So we're going to begin looking at the scalar and vector products, and in this video we're going to look at the scalar product, which is also called the dot product. So in our previous lessons we've looked at addition, subtraction and multiplication by a scalar, but we haven't talked about multiplying vectors. And there are actually two methods for multiplying vectors. There's what's known as the dot product or the scalar product, and then there's the cross product, also known as the vector product. So our dot product or scalar product is obtained when we multiply a vector by another vector. It's called a scalar product because the result is a scalar. So the answer has no direction, just magnitude. And this is the notation. We write u dot v. Now if we have two-dimensional vectors, so u has components u1 and u2, and v has components v1 and v2, then the dot product is obtained by multiplying the like components together and then adding them. And in 3D, it's just extended. So here's a simple example. Find the scalar product for the vectors p and q. So we're going to do 1 times 5 plus 3 times negative 1. And that gives us 2. So you're probably thinking, well, what does it really mean? It's all very easy to learn a formula to calculate something. Now the dot product uses like components to find out how similar two vectors are. We can actually use the dot product to find the angle between two vectors. We'll have a look at that a little bit later on. If we consider the vectors A, which has components 0, 1, and B, which has components 1 and 0, and they represent unit vectors in the northerly and easterly directions respectively. Have a look at this one here. This is 0 units across, 1 unit up, and this one is 1 unit across, 0 units up. Then these vectors have nothing in common at all. They're actually perpendicular to one another. So not surprisingly, the dot product is 0. Now let's consider a unit vector in the northeasterly direction. So vector C has components 1 on root 2, 1 on root 2. Now, if we look at vector C and vector A, they do have some similarity. They've both got some northness about them. So if we do the dot product, we end up with 71%. There is some similarity between these vectors. Now, if we look at the various components of two 3D vectors, we can see we've got I, J, and K there, the base unit vectors, for both of them. If we compare like components, we're using the dot product. And if we compare unlike components, we actually use those for the cross product. We'll look at that in the next lesson. Now we have the following relationships. U dot V is exactly the same as V dot U. U dot U is equal to the magnitude of U all squared. And we're going to use this relationship all the time when we get to vector proof. We can expand. U dot brackets V plus W is the same as U dot V plus U dot W. And you probably know where I'm going next. FOIL. So we can do U dot X plus U dot Y plus V dot X plus V dot Y and expand those brackets out. And probably the most common application of the dot product is to find the angle between two vectors. And what we actually do is use the cosine rule. So we're going to consider the vectors u and v, and I'm going to translate the vectors so they begin at the same point. Now the vector from the head of v to the head of u is u minus v. Let's use cosine rule. We have got magnitude of u minus v all squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times magnitude u magnitude v cos theta. Now this here is one of those identities that we just looked at. The magnitude of u minus v all squared is equal to u minus v dot u minus v. And we can expand this out using FOIL. Now I've done some simplification here. U dot u is magnitude of u squared, and v dot v is the magnitude of v all squared. And this one here comes from the outer and inner products because order is not important with the dot product. Right, we can do some cancelling. We end up with negative 2 u dot v is equal to negative 2 magnitude of u magnitude of v cos theta. Dividing both sides by negative 2, we end up with u dot v is equal to magnitude of u magnitude of v cos theta. And so the angle between two vectors u and v is found using either u dot v is equal to magnitude of u magnitude of v cos theta, or we can rearrange this and make cos theta the subject. And as an important note, the angle is always taken between 0 and 180 degrees rather than using a negative or a reflex angle. Let's look at an example. Find the angle between the vectors I minus 2j plus k and 3i plus 2k. So here's our equation. We want to figure out the dot product and the magnitudes of both of those vectors. So remember, our dot product is going to be 1 times 3 minus 2 times 0 plus 1 times 2. And magnitude of this vector is the square root of 1 squared plus negative 2 all squared plus 1 squared, which is 6. And the magnitude of this vector is the square root of 3 squared plus 2 squared, which is 13. Into the calculator, and inverse cos, the angle between the vectors is 56 degrees. Now we talked about when the dot product is 0 before. For non-zero vectors u and v, if u dot v is equal to 0, then u and v are perpendicular vectors. Now, in geometric space, we call that orthogonal vectors. Let's have a look at the proof. If two lines are perpendicular, the angle between them is 90 degrees. So looking at our formula, u dot v is equal to magnitude of u, magnitude of v, cos 90. Cos 90, of course, is 0. So the dot product is equal to 0 if the vectors are perpendicular. Here's a past exam question. The vectors a and b are perpendicular to each other. Find the value of k. So we're going to work out the dot product and put it equal to 0. So 4 multiplied by k plus 3 plus 2k is equal to 0. Expand and simplify. K is equal to negative 2. So we talked about perpendicular vectors. What about parallel vectors? For non-zero vectors u and v, if the absolute value of u dot v is equal to the magnitude of u multiplied by the magnitude of v, then u and v are parallel vectors. Let's look at the proof. If two lines are parallel, the angle between them is either 0 or 180 degrees. If it's 0, then substituting that into our formula, cos 0 is 1. So u dot v must be equal to magnitude of u multiplied by magnitude of v. If the angle is 180 degrees, cos 180 is negative 1. And so u dot v is equal to negative magnitude of u magnitude of v. In other words, u dot v is equal to plus or minus magnitude of u magnitude of v. And we can write that using absolute value signs. So there's our proof. Now it's really worth pointing out here, this is a scalar, and so these signs here are absolute value signs. That strips the negative off. These are vectors, and so these signs here represent the magnitude of the vector. So here's an example. Suppose u and v are parallel, and their lengths are 4 and 5 respectively. What are the possible values of u dot v? So here's our formula. Absolute value of u dot v is equal to magnitude of u magnitude of v. So we know the lengths are 4 and 5. So the absolute value of the dot product is 4 times 5, which is 20. So the dot product could have been plus 20 or minus 20. Let's finish off with a past exam question. Vectors a and b are defined as a, which has components 1, 1 and t, and b has components 0, negative t and 4t. Part A, find and simplify an expression for A dot B in terms of t. So that's nice and easy. Let's multiply the like components and add them together. So we've got 1 multiplied by negative t plus t times 4t, which is negative t plus 4t squared. Part B, hence or otherwise find the values of t for which the angle between A and B is obtuse. Now if the angle is obtuse, then cos theta will be negative. But let's start with the formula, and we're going to substitute in what we know. We know the dot product, and the magnitude of A would be square root of 1 squared plus 1 squared plus t squared, and the magnitude of B is the square root of negative t all squared plus 4t all squared. And tidying that up, we have this. Because we want an obtuse angle, we want cos theta to be less than 0, so we need to solve this inequation here. Because the denominator is positive, I can multiply both sides by this denominator, which is going to give us negative t plus 4t squared is less than 0, and I've just turned that around. Right, we've got to solve this quadratic inequality. Let's factorize. The critical values are 0 and 1/4, so let's draw up a little diagram. So we've got 0 and 1/4. Now if we imagine this to be a parabola, which it is, I'm just going to draw that in. We want to know when that parabola dips below the x-axis, which is in between here. So our solution is 0 is less than t is less than 1/4. Okay, that's it for the dot product. In our next lesson, we're going to look at the cross product.